Now that we know how to fit a simple linear regression model to a dataset, let us now discuss how we can assess the accuracy of the model, or in other words, how we can assess the goodness of fit. Now remember, we have a data which is scattered like so, and we have fitted a straight line to this dataset, right? So some amount of misfit will always be there because of these distances of the points from the predicted value which is given by the straight line. So these distances of these points from the straight line is what we have been calling as residuals, the epsilons. So because of these epsilons, some amount of misfit will always be there. This, in a cumulative sense, therefore, if I can measure all these misfit values, then the standard deviation of these epsilons, epsilon i's, that will tell us how good the model is. So the standard deviation of the error term, which we have been denoting by the symbol sigma. So this is because of epsilon i's, the misfit is because of epsilon i's, which we have been calling as residuals, and the standard deviation of the epsilon is, well, we have been writing epsilon as white noise, so normal with mean 0 and variance sigma square. So this sigma is the standard deviation of these residuals, which means that it is the average amount of deviation from the regression line, right? And more importantly, it takes into account the variability that cannot be explained by the model. So therefore, RSE, if I may call it, the lack of fit, I can define as RSE, which is nothing but sigma hat, and that is from our earlier derived expressions. So sigma hat square was RSS divided by n minus 2. If we take the square root of that, so that would be sigma hat. The square root of the variance of the error term would be the RSE, residual sum of error, right? So this in some sense is giving a lack of fit. Essentially, RSE is the variability that remains in Y after accounting for the effect of X. It is the variability that cannot be explained by the model. So it's the variability that remains in Y after removing linear effects of X. All right. And this is also intuitive because you see, if all the predicted values were very close to the observed value, then yi minus yi hat square, the denominator, the numerator would have been very small. So sigma hat as a result would be small. Your model would be good. If on the other hand, the predicted values, well, one of them or many of them are far away from the actual observation, yi. So yi minus yi hat square will be large, and therefore sigma hat square will also be large. So sigma hat therefore denotes the lack of fit. Okay. So we can use sigma hat as an index to assess how good our model is. If sigma hat is large, we'll say our model is a poor model. But what is the disadvantage of using this term RAC, residual sum of errors? The disadvantage is the fact that it is not scale free. It depends on the unit of y, because the numerator will have a unit. So this depends on the unit of y. This is not a scale-free measure. And we had, in the context of covariance and correlation, we had discussed this. We would want an index which is scale-free. In order to arrive at a scale-free index for assessing the accuracy of a simple linear regression model, we use an index which is called the coefficient of determination. And this we write as TSS minus RSS divided by TSS, where, of course, RSS we already know is the residual sum of squares, which is nothing but sum of all the differences, sum of squares of all the differences between the observed and predicted values, right? So TSS minus RSS divided by TSS is called the coefficient of determination, and I'm telling you that it's a scale-free measure of how good the model is doing. Let us look at carefully why that is the case. So TSS is essentially the total sum of squares, which represents the total variability in y. See, this is nothing but the numerator of the expression of for variance of y, right? Variance of y would be summation of yi minus y bar square divided by n minus 1, right? So that would be variance. I'm using just the numerator of the variance. So TSS represents the total variability in y. RSS represents the lack of it, how poor, what is remaining after the effect of x has been removed, right? That's what RSS is giving us. So TSS minus RSS, this numerator here, TSS minus RSS, is essentially the variability in y, which is explained by the linear effects of x. Let me write that down. So this is the variability in y that is explained by linear effects of x. And I am standardizing it by the total variability. So therefore, R square is limited now. It can lie only between 0 and 1. When RSS is as large as the total variability in y itself, nothing can be explained by x. Then you will have an R square which is 0. And when all of the variability in y can be explained by linear effects of x, then R square would be 1. You have the best model. Okay, so therefore R square represents the fraction, the proportion of variability in y that can be explained by linear effects of x. And hence R square, the coefficient of determination, is a good choice for assessing the accuracy or goodness of fit of the model. It's also scale free because we have units in both the numerator and the denominator that gets cancelled out. We have standardized it, so it now lies between two fixed values, 0 and 1, right? So therefore R square, the coefficient of determination, appears to be a good choice for the goodness of fit of a simple linear regression model. In fact, for a simple linear regression model, one can actually show that this capital R square turns out to be little rxy square, What is little rxy? Little rxy was our correlation coefficient, which we had seen earlier. We had denoted it by sxy divided by square root of sxx and square root of syy. In fact, this can be proved. So you can prove that the coefficient of determination for simple linear regression turns out to be the square of the correlation coefficient. So this I leave as a homework for you. Homework, prove it. And again hint, in order to prove it, for simplicity, you may assume that x bar equal to y bar equal to 0. Of course, this holds true when they are not 0 also, but it will be easier for you to prove it if you assume that the average of x and average of y both are equal to 0. So this is how we assess the goodness of fit of simple linear regression model. So in simple linear regression, it is possible to get a confidence interval of the mean response. Recall that the mean response is given by this straight line, where at each given level of x, this value would be mu y given x. This value would be mu y given x equal to x2 and so on. So again, recall y given x is normal with mean beta naught plus beta 1 times x and variance sigma square. The mean response, predicted mean response, is beta naught hat plus beta 1 hat times x naught, if we are talking about the level x equal to x naught. We can get a 100 into 1 minus alpha % confidence interval around this mean response mu hat, and that would be given by, again using the same generic expression, estimate plus minus critical value times the standard error of the estimate. So this is basically nothing but the standard error of mu hat y given x equal to x naught. This is of course our critical value, and this is the mean predicted mean response, which is nothing but beta naught hat plus beta 1 hat x naught. So therefore, at the level x equal to x naught, we'll get a predicted mean response. Not only will we get a point estimate value of the predicted mean response, which is this, but we'll also get a confidence interval around it. So in the previous slide, we had looked at the confidence interval of the mean response. Now remember, instead of obtaining just the mean response, one may obtain any value from this distribution, right? Any predicted value y. So a simple linear regression model can be used to make a prediction of a new response also for a given new level of x. And for the prediction, note that I'm also using a superscript f. So of course the predicted response would be based on the straight line that we have fitted. So y naught f hat would be equal to beta naught hat plus beta 1 hat times the new x naught hat, x naught f. Now this is the point estimator of the new response, and we can build a confidence interval around this new response also. So the new responses confidence interval, which is no longer called a confidence interval, but it's called a prediction interval. So we are giving a prediction interval around a new y. Note that in the previous case we were talking about confidence interval around the mean response mu y given x. Here in prediction interval we are talking about a prediction interval around a new y, right? That happens to be again the point estimate plus and minus the critical value times the standard error of that estimate. Now we see, if you compare the expressions given in the previous slide for confidence interval with this one, which is for the prediction interval, we would see that there is an extra term here, which is this sigma square hat into 1. So this means that there is an additional variability which is associated with the prediction interval, and therefore the prediction interval is wider than the confidence interval around the mean. And this is also intuitive because when we are talking about confidence interval around the mean response, it is these points that are of concern to us. However, when we are talking about prediction interval, we are talking about a value of y generated from this distribution. So therefore, this additional amount of variability in y also comes into picture, and therefore this variability in y, the variance of y, is also sigma square. So therefore the sigma hat square is an additional term which comes in the prediction interval, and therefore prediction intervals are wider than confidence interval. Indeed, using the expressions of confidence interval and prediction interval, if for a given data set one plots the prediction interval and the confidence interval, one can see that the solid lines, the solid lines gives the confidence interval of the mean response of y, and the dotted lines, so this interval is giving the prediction interval for individual y given a certain level of x, which is xp. And obviously we see that, as expected, the confidence interval around the mean response is narrower than the prediction interval for individual y. That's of course one observation we make from this figure. What else can we observe from this figure? Another interesting thing that we observe and note from this figure is the fact that these confidence intervals and also the prediction interval, they become narrow in the central region and wider as we move further and further away from the mean. This figure tells us that simple linear regression model is a model around the mean. So SLR is a model around the mean. The closer you are to the mean of x and y, x bar and y bar, the more accurate, there are greater chances for you to be more accurate, more precise. The farther we move away from the means along these directions, we see that the confidence interval gets wider and wider, which means that there is less and less precision in our estimates. So hence, simple linear regression model is a model around the mean. It is meant for mean or bulk around the mean of a distribution, and therefore obviously it's not meant for values which are supposed to be extremes in some sense, right? So what I mean by that is, if we have suppose rainfall as a variable of interest, then bulk of the rainfall values, which means if you take seasonal average or annual average, then, and let's say your predictor is some atmospheric variable. So some atmospheric variable is your x and rainfall is your y. Then the seasonal mean rainfall or the annual mean rainfall is a variable to which we can fit a simple linear regression model. However, if the variable of interest is, let's say, the extremes, for example, the maximum value in a year or a value which exceeds a very high threshold, in that kind of situation, simple linear regression model may not be a good choice of model because it's meant to be a model around the mean.